It's my great pleasure to introduce the next speaker, Mark Embree. But before I get to that, I should mention that...
I think that's the wrong...
Okay.
That's the wrong slide.
Sorry, one moment. Can I leave it to you to fix it as I... Okay, they're putting on the right lecture, but I'll continue with the introduction. So I should first mention that this is the third installment in the IWOTA Israel Gohberg lecture series. This lecture series was initiated in 2017 by the IWOTA Steering Committee and the International Linear Algebra Society in recognition of the many influential contributions of Israel Gohberg to the operator theory community, as well as to linear algebra and many other fields. Many of you have known Israel and know how influential he's been, not just in operator theory. So, first lecture was at IWOTA in 2021, Vern Paulsen. Next one was in ILAS 2022, Paul van Doorn, and we're very happy to have Mark Embree as the third lecture in this series this year. So Mark got his PhD from Oxford in 2000 under Andrew Watton. He stayed on for another year, I think, working with Nick Trevethan, and then he moved to Rice University in the United States, where he stayed for more than a decade. So since 2014, he's been at Virginia Tech as a full professor and leader of the Computational Modeling and Data Analysis program. He's known for his excellent work in numerical analysis and numerical linear algebra, in particular spectral behavior, eigenvalue problems of all sorts of interesting operators, and I think maybe most notably his book on spectra and pseudospectra with Nick Trevethan. He also has a lot of very nice work in large-scale systems and model reduction, and has been very involved in lots of SCIEM activities, also on editorial boards of many SCIEM journals. So I promised I would keep it short. I'm getting there. So as a last part, I want to mention as a small advertisement that he's also part of the organizing team behind ILAS 2026. And with that, I'll hand over to Mark, who's going to talk about contour integral eigensolvers through the lens of system identification. Please go ahead.
Thank you very much, Sanne. Thank you to... Thank you. Thank you also to Ian and to the rest of the organizing committee for putting on this great meeting. Also to the Gohberg Lecture Committee. Thank you for the opportunity to come and speak about, I think, some topics that would fall at the intersection of a few of the many topics that were of interest to Israel Gohberg. And I'll take a pause in a little bit of a few minutes here in the lecture to reflect upon Gohberg's connection to one aspect of this talk. This work is primarily with my former master student Michael Brennan and my colleague Serkan Guershen, and with a few helpful words of advice from Joe Ball, as anyone in Blacksburg should have such a resource available. It's fortunate for that. Some students who are working on part of this problem involving sensitivity of eigenvalues and decay of singular values of Loewner matrices, and my colleague Cosmin Onicha at MathWorks, and then Jonathan Baker and Jennifer Green, who worked on the last part of this talk, spiderweb problems that tie in nicely with the metric graphs that we just heard about. And so without further ado, let me start at a very basic level. We're going to compute some eigenvalues. Everything I talk about here will be finite dimensional, but that doesn't necessarily mean finitely many eigenvalues. So if we start with a square matrix and we want to compute its eigenvalues, of course we'll compute up to n eigenvalues. We can generalize this a little bit to a matrix pencil problem. We then get n eigenvalues, unless this matrix E is a little strange. Maybe it's singular, in which case we have an infinite eigenvalue, or we could have a singular pencil, in which case the entire complex plane is an eigenvalue. But those are monsters that we generally want to avoid. So we're generally thinking of up to n eigenvalues here. Of course, it was of great interest to Professor Gohberg to generalize to matrix polynomials. And so if we have a degree d polynomial in the eigenvalue parameter, then we could have d times n eigenvalues. And of course, one way to solve this is to turn this into a dn by dn matrix. And there are all kinds of interesting questions about root vectors and so forth associated with these problems. But we can go one level further and think about more general nonlinear eigenvalue problems, which would approximate with a polynomial. I think Melina Freitag will talk about this tomorrow morning. We can then ask how many eigenvalues do there exist now? Well, you might think if you extrapolate the polynomial problem to infinite degree, it's no surprise that there could be infinitely many eigenvalues of these nonlinear eigenvalue problems, even in dimension 1. Just a basic root finding problem. We could go a step further and allow nonlinear dependence in the eigenvector. Those are very hard and important problems that cleverer people than I are looking at. Just an example to kind of motivate things. This is a finite dimensional problem from a delay differential equation. We might want to determine rightmost eigenvalues to see if the problem is asymptotically stable or not. And because there are infinitely many eigenvalues, we have to just give up hope of computing all of them, right? For a large-scale matrix, we might find that unappealing, but for a nonlinear problem, it's absolutely essential that we zero in along some region of the complex plane. And there are a variety of different techniques based on Newton's method or on approximating the nonlinear function with a polynomial, a rational function, and so forth. Today, I'm going to talk about a class of algorithms based on contour integration. So we want an algorithm that will go hunting for all of the eigenvalues that fall within this ellipse. And most of these methods can be motivated by just a very, very simple classical idea. Take the formula for a spectral projector, and I'll write it here for a general matrix and not for the sort of a nonlinear problem. I'll go back and forth between resolvents for that linear eigenvalue problem and T of z inverse for the nonlinear problem as appropriate. But if we take that formula for the spectral projector onto the eigenvalues within omega, a numerical analyst would naturally think, how can we approximate this with a quadrature rule? So we take some weights and we evaluate the resolvent at certain points and we add that all up and we get an estimate of that spectral projector. And there are a series of algorithms that have become very popular within the past 25 years that apply similar techniques. A large class of them are based on system identification in a way that I will describe in the bulk of this talk. But I wanted to also acknowledge that there are other methods that are based on getting an approximate spectral projector and then doing some kind of Rayleigh-Ritz approximation, generating something that can be iterated upon to get a refined version of the estimate to eigenvectors. And there's a whole wealth of work that's been done on that class of algorithms. But we're going to really focus on the system identification class of algorithms. That's what I've looked at more. And of course, I think that's a little more relevant maybe here to the IWOTA audience. Resolvents play a key role in all of this. So maybe just to calibrate our thinking a little bit, let's just look at a simple 3x3 example. We write down a matrix A. We could compute its characteristic polynomial and find its roots. That's a bad way to compute eigenvalues in general, unless you have a small matrix. But we do see that characteristic polynomial emerging in the formula for the resolvent. So we really think of the resolvent as a matrix of rational functions in this case. And we have the characteristic polynomial falling on the denominator there. And so we can see that, of course, the eigenvalues are the poles of the resolvent. At least one entry in the resolvent will blow up at every eigenvalue. And I've chosen an upper triangular matrix to give this a nice structure there. So let's look at some pictures. I'll try to show you a lot of pictures here this morning. Here's a plot of the norm of the resolvent in the complex plane. So we have the real part and the imaginary part of the parameter z, and then we look at its height on a logarithmic scale. And if you want to compute these kinds of things for yourselves, there's a wonderful package called EigTool, written by Tom Wright, that's mostly still working very well despite its vintage. It's a remarkable piece of code that Tom developed. And it can use to make 3D plots like this as well. I often look at things called pseudospectra, and I won't say a whole lot about them today, but just a little marketing here. You get the epsilon pseudospectrum by taking a slice of level 1 over epsilon through this resolvent surface. So there's 1, there's another, and there's another. And so if we look at the sets that are formed by those intersections, we can show the boundaries here. The lowest level gave us the largest of those regions, and then the second level gave us that figure 8 and a little circle around the other eigenvalue, and then if we get even smaller, we see the 3 individual spikes in our resolvent landscape emerging there. And this is the epsilon pseudospectra, 3 epsilon pseudospectra for this particular 3x3 matrix. Okay. But you know, if we're thinking of large-scale problems, maybe, you know, looking at the entire resolvent is going to be too expensive. And so what the cool kids do now in the numerical linear algebra world is they sketch. And by that we mean that instead of looking at the entire resolvent, we'll look at a random vector applied to the left and applied to the right. And then we can look at what that function looks like. It's a scalar valued function now. And we see it also has poles in the right places. Sometimes they're pretty subtle, but there's a little pole there in the upper right where we'd expect one. And this maybe suggests that, you know, different random vectors will give us different aspects of the resolvent. We'll look at this little simple 2x2 case and think about sketching it. And of course, if we pick our left and right directions properly, we see both of the eigenvalues emerging as poles there. But if we pick our left and right vectors incorrectly, we might miss an eigenvalue, like we almost did in that upper right plot, where in this case the z equals 1 eigenvalue doesn't show up. And of course, those of you conversant in control theory will say this is just a kind of reachability and observability condition that we see there. So the point here is that if we want to sketch, we need to be a little bit clever in the way we do that. And we need to pick our left and right directions intelligently, or at least not hazardously. So we might think about 2 different approaches of compressing dimensions of spectral problems here. One is to sketch the resolvent as we've just done, but maybe not in one direction, maybe in k directions here, where we'll want to pick a block of random vectors, say. That's usually a safe way to avoid catastrophe. And so we get our n by n matrix compressed down to a k by k matrix. But the individual entries in that k by k matrix are order n rational functions, and we could find n poles there. And those poles will exactly match the eigenvalues of A. But if we want to play this game, we've got to compute that resolvent, which means we've got to be able to invert an n by n matrix. Contrast this idea of sketching the resolvent by looking at the resolvent of a sketched matrix, where we take our matrix A and we compress its dimension down to a k by k matrix, and then we look at its resolvent. This is what might happen in a kind of Galerkin projection or Petrov-Galerkin projection method, where we have a high-dimensional operator that we compress down to low dimensions. Now we have only k eigenvalues of this compressed problem. They won't generally match the eigenvalues of A, but it's fast to work with once we find this L and R, because we can then invert that k by k matrix quickly. So all the work here goes into finding a strategic choice of L and R and not just choosing them randomly. So these are sort of 2 different modes to operate in. We're focusing on the top one today. Contour integral methods, that's exactly what we're doing. Krylov projection methods fall into this second class. Okay, and I think what I want to focus on here this morning is to view this contour integral problem through the lens of system identification. And to do that, I'm going to think about a dynamical system driven by our A matrix that we care about and our sketching matrices R and L. Now, of course, we can compute the Laplace transform of the dynamical system, and we can get out a transfer function, h of z. We can consider reachability and observability of these sets and think about when we're able to recover all of the eigenvalues of A in that kind of language. So we have an eigenvalue problem where maybe we want to sample h of z to find its poles and then thus recover the eigenvalues of A. But to a systems theorist, that sounds a lot like a system identification problem. We want to use samples of H to recover our system matrix A and our input and output matrices R and L star in some coordinate system, some minimum realization. And so we can take that dynamical system and we can realize this in many different ways. So if I take any invertible matrix S and I apply it on the left, and I substitute the identity in the middle here, then I have transformed a coordinate system, and I have an equivalent realization where I can see A, R, and L star, or S, A, S inverse, and so forth. And so that choice of S doesn't change my H of Z. So if I'm in this system identification world, I have to satisfy myself that I'm only going to recover these matrices up to some similarity transformation. But we're going to actually be able to exploit that to come up with some good algorithms. Okay, so let me plunge into what those algorithms look like. So to begin with, let's assume everything in this world is diagonalizable. And I know a lot of Gohberg's work was really focused on chains of root vectors and other interesting properties there. So I hope this accommodation is acceptable. So let's suppose we want to find some eigenvalues, m of them in omega. We want to avoid the other eigenvalues. So I'll write the spectral decomposition of A as these two sums where I want to find one part and not the other. So I have what I will call wanted and unwanted eigenvalues. If I look at the resolvent, I get the same kinds of expressions, a wanted portion of the resolvent and then an unwanted portion. So we can write this kind of graphically here. Some block of eigenvectors we're trying to compute, some resolvent of a compressed matrix lambda that contains the eigenvalues we want, and then the other eigenvectors, the left eigenvectors in W star. And then a block of stuff we don't care about, that we don't want to get in the way. In some sense, we can maybe access Zi minus A inverse, and we'd like to discover what lambda is without worrying about the red stuff slowing us down. Now, Keldysh in the 1950s extended this to this kind of perspective to nonlinear eigenvalue problems, where we can write that same block of eigenvectors, a resolvent for our diagonal matrix of eigenvalues, and then the left eigenvectors, and then a nonlinear portion that is analytic in the set that we're looking at and then contains all the other spectral stuff outside of omega, has poles there. But within omega, it just kind of patches up the nonlinearity while we let the blue matrices here capture the structure that we want to compute. And of course, let's think a little bit about Keldysh's work here. So here's an example of a nonlinear eigenvalue problem, a 6x6 nonlinear operator here, but with infinitely many eigenvalues. I'll talk about where this came from in a little bit. We have some multiplicity 2 eigenvalues, the red ones here. We have some multiplicity 1 eigenvalues. Though multiplicity 2 eigenvalues are derogatory, there's a two-dimensional kernel associated with T of lambda j. And we have to normalize the eigenvectors in an appropriate way. And Keldysh would go into how to handle Jordan chains in this setting, but everything we're dealing with is our semi-simple eigenvalues. Here's what that plot of the norm of the resolvent looks like in this case. We see poles happening at all of these real eigenvalues. And what Keldysh's theorem gets us is, pick the region we want to compute. There are 4 eigenvalues in there, 2 singles, 1 double. Look at that contour with that ellipse imposed. And then we want to break out the piece that we seek to compute. And then what's left over here is nice and smooth in omega. Okay, so that's the key picture to have in mind. Separate out the poles from the piece that we don't particularly care about. Okay, so Keldysh's work was published in 1951 in a short 4-page paper that's published in Russian. And in, well, I think certainly the first important book on non-self-adjoint operators, Gohberg and Krein, talk about this paper by Keldysh. In chapter 5, they say this chapter apparently contains the first adequately detailed treatment of the fundamental results of M.V. Keldysh on the theory of non-self-adjoint operators. And they go in and they're looking at polynomial operators, like I mentioned earlier here, and they're looking at linearizations of those polynomials and root vectors and so forth. And they go into that in I think it's section 9 of chapter 5. But if you want to get a little more of the backstory, there's a fascinating essay in the 60th birthday conference for Israel Gohberg. A few of you, I think, in this room were there at that conference. Yes, okay, so you'll remember this. In Calgary, Canada, 1989. And one of the sessions was a plenary talk given by Gohberg called Mathematical Tales and Gossips. Now, what shows up in the proceedings is simply called mathematical tales, so I don't know if the gossips got truncated from the published account. I don't think they recorded talks in those days, but in any case, we get a little bit of a background on that section of Gohberg and Krein. We decided to include in the book a number of very interesting recent results of Keldysh on completeness and distribution of eigenvalues. These results were published without proofs in a 4-page short note in Doklady. We tried to get the proofs from the author, but were informed that they do not exist. The detailed manuscript with proofs disappeared. Okay, at the time, Keldysh was president of the Academy of Sciences of the USSR. He was responsible for the theoretical part of the USSR Cosmos project. In official reports in the reminiscences of the first cosmonauts, there were 2 persons who were not called by their real names. These were the chief designer and the chief theoretician. We all knew that Keldysh was the chief theoretician. During these years, Keldysh was very busy, and there's no chance that he would have time to recover the proofs of his results. With the help of some colleagues, we recovered the proofs of an important part of these results, so for the first time, these results with complete proofs appeared in our first book. The original manuscript of Keldysh was found much later, I don't know the circumstances, and was published in 1971. So that's why we have 2 citations there for the Keldysh paper. There's a much longer 20-plus page paper. And indeed, part of that 1971 paper shows up on a postage stamp of Keldysh. I don't know if you can see it right above the 12. There's maybe the first instance of latex showing up on a postage stamp. And the formula, the sum of 1 over hi to the rho is less than infinity, is just simply one of the conditions in one of his proofs in that paper. So IWOTA friendly content has showed up in the postal system. Okay, so let's go back to our contour integrals. Why are we breaking these problems up like this? Well, because contour integration gives us the key to isolate the part of this problem that we care about. So by integrating around that desired region that we seek, we recover the blue part of that spectral decomposition. And all of the red part with its poles outside of omega goes away. And the same is true for the nonlinear problem due to Keldysh's theorem. That n of z term integrates to 0. And so we can evaluate the transfer function. We can evaluate any function through a resolvent integral and then find out what f of lambda is. And so this gives us a tool, if we can compute these integrals, for sampling all kinds of information about our function. So there are 3 key insights that turn this into a practical algorithm. And the first is that those integrals need to be approximated by quadrature. Typically we're on a circle or an ellipse, some friendly domain like that, and the trapezoid rule is exponentially convergent and is a lovely tool to use. So there's not a lot of work that goes into fancy quadrature rules for these problems. But still, even if we wanted to implement that quadrature formula, we have that large n by n resolvent, and to compute the inverse of that n by n parameter-dependent problem would be prohibitive for large problems. So sketching gives us a way of taking that down to some smaller k by k dimension. And then what's one of the nice appealing properties of this class of methods, quickly pointed out early in its history, is that these solves can be computed independently. By solves, I mean the application of an inverse to a vector. We don't actually compute the inverse numerically. We would solve a linear system with Gaussian elimination, or even for large-scale problems with an iterative solver. And that can be done in parallel for all of these different quadrature points. So these are very friendly algorithms. And what's more is that we can choose different f. And once we've done this hard work of computing the quadrature, changing f is easy. So just different weighted sums of your quadrature data give you different function evaluations. And it's our goal to use such function evaluations to discover the lambda, the v, and the w. So the idea, we can sample these kinds of functions by a quadrature rule for a sketched resolvent, and that will allow us to find the eigenvalues that we want. Okay, so as I said, computing these system solves is the bulk of the work. We can use different f very easily. Most of the algorithms to date only choose monomials for f of z. They're computing moments of these, classical moments of these problems, but we can get into some numerical issues if we have large domains omega, many eigenvalues, high powers of p. And so by looking at this problem and saying these contour algorithms are really just doing system identification, that gives us a way to unlock a variety of new rational interpolation-based system identification algorithms to use different f, which don't cost any more to use, to recover the eigenvalues we want. And not to recover the sketched eigenvectors, but to actually get the input-output matrices, the full eigenvectors. Okay, so here's the key strategy. That we're going to take this problem that it's a dynamical system that's driven by data that we don't know, that we're trying to find, lambda, w, and v. And we're going to try to take some data that we do know. We're going to collect data in these blue matrices, D and DS, B and C. And we're going to use that data we can measure to transform this dynamical system into one that exposes, in a more friendly way, the eigenvalues and eigenvectors. The assumption about the data that we're going to collect is that it can be factored into the product of O and R matrices, observability and reachability, if you will, and O lambda and R, and O and W star and V and R. Now your complaint might be, we don't know W and lambda and V, so what's the good of this? These factorizations just need to exist in theory. We will just be working with the data that we can measure in blue. We don't know how to do these factorizations necessarily. That's not, they just exist as scaffolding. The important point, though, is that these matrices will have to be full rank. Okay, so 4 steps will get us there. First, just write down that system that we want to identify. Change coordinates. Replace the state vector x with some new state vector r times y times c. Now, I don't know what r is. I need to say where y comes from. We need to take the economy size singular value decomposition of that data matrix D. So we can compute D, and once we have D in hand, we can compute its SVD. Now, that's assuming we can determine its rank. What is D? I'm going to tell you what D is. Right now, it's just a data matrix. I'm about to tell you. You can have choices. Yeah, good. Fair, very fair question. I'm going to try to show one framework that will work for a variety of different methods. So suppose we have this D, and we can compute its SVD. We write down our original system. We change coordinates using that matrix of singular vectors y. So we have an equivalent system, because this r times y is an m by m invertible matrix. Now we're going to pre-multiply on the left by another invertible matrix, x star O. And now my assumption was that I had not only a D matrix, but a D sub S matrix, another data matrix that has this form. So taking on faith that there exists such a matrix, then, we've got x star O R Y, which if we go back up to our singular value decomposition is just the matrix of singular values, sigma, times a state variable prime, times singular vectors, another data matrix we can measure, singular vectors, our state vector, and other objects that we can measure, either singular vectors we compute from D or data matrices B and C. Now, I have to tell you what these data matrices are to prove that they actually, good choices exist. But supposing that we can meet those criteria on the last slide, we have now transformed the system to an equivalent system whose state matrices are all given to us by things that we can measure. And so the two equivalent systems, they must have the same transfer function. Poles of the first version have to be poles of the second version. So we can identify the eigenvalues and eigenvectors from that second system, and they have to match the ones that we can't see in the first system. So the idea is just to do a basic transformation of the problem to make it tractable. Okay, and then we can also back out the eigenvectors V and W once we get the eigenvalues. So we need to compute eigenvalues of a matrix pencil. Where do the matrices come from? Here's your, okay, fair question. You anticipated it. Okay, we're going to construct data matrices by taking tangential samples of our transfer function or its derivatives. So we're going to find different ways of computing those through contour integration. Okay, so with enough data and exact numerics, we will recover the exact eigenvalues, but our results are going to vary. So all of these different approaches will all give you, in theory, the exact same eigenvalues, but there's a potential use of different algorithms because every different algorithm will handle inexact data a little differently. And so we have to think about not just eigenvalues of matrix pencils, but how perturbed coefficient matrices affect those eigenvalues. Okay, so let me tell you about the classical approach. Here we're going to use moments. So just samples of expansion of our function at infinity or expansion of our function at a finite point. This is another approach that we can now introduce by viewing this approach through the lens of systems theory. So if we integrate with f of z equals minus z minus mu to the minus p plus 1, we can compute the coefficients in the Taylor series of the transfer function at any finite point, not just at the point at infinity that only required powers. But we can also construct interpolants to our transfer function at other points and just do simple linear interpolation, but at many different points, first order interpolation at many different points. Okay, so the classical approach. We're going to build a data matrix that's made up of powers of our lambda with our eigenvectors on either side, which we can get by just multiplying t of z inverse or zi minus a inverse against z to the p. So for example, in that case, the data matrix will be a block Hankel matrix. The ds matrix is a shifted Hankel matrix, and our b and c come from that same data. Now we have some conditions. We need to make sure that D has the correct rank, has rank M. Could be deficient in rank if we don't have a large enough D or if we have some derogatory eigenvalues or so forth. And we could also get some numerical results if we end up having to use high order moments. So just to show you that this factorization that I claimed actually exists, here are those 2x2 block matrices that I showed you earlier. And we write out the form for the moments M0, M1, M2, and so forth, with just the powers of lambda on the right, just the formula for MP. That's all data that we can compute through contour integration. And then we simply observe that we can come up with a factorization into the product of two matrices, full rank matrices, on the left and right. And we'll call those this O and this R that appeared earlier. Now, we need this DS matrix, which is a shifted Hankel matrix, to have a very similar property, but now with a lambda in the middle. We see where that lambda comes from, just higher powers of lambda in this matrix, so factor that out in the middle. And then similarly, B and C have the required form. They're just our O and R matrices with eigenvectors on one side or the other. Okay, so this template I showed you is satisfied at least in this classical case. But one can realize then, going back to classic systems identification literature, that this method turns out to be just the Ho-Kalman algorithm for system identification back from 1966. And if we go back to the paper by Ho and Kalman, we can look and see there's a Hankel matrix there, and there's a shifted Hankel matrix, which is a little blurry to see there, but it exists. And then there's something here that looks like a kind of take on the singular value decomposition with some sigma inverses in the midst. And then that allows us to get a recovered system, which is exactly the recovered system that we have through this contour integral algorithm to recover those eigenvalues. So these class of methods just boil down to Ho-Kalman applied to this contour integral data. But there are these other choices. So if we want to do an expansion of our transfer function at a finite point, mu, then we just have to integrate our resolvent data with different function f, and we can recover now different matrices here, and same caveats apply. Now we have an extra parameter to choose. How do you pick mu to give us good results? Do the factorizations exist? Well, we can take this matrix D and we can factor it into two matrices here, the O and the R. To get to ds, we go through a matrix D0 that involves actually lower order derivatives there. So we get a central factor, mu I minus lambda, and then we can combine D and D0. We get out the factorization we want for this ds matrix. So we have a way of computing that. And then we have our B and C matrices. So again, another another case that satisfies this same template that we required for these contour integral algorithms to work in a system identification sense. A third one, my colleague Serkan Gurershin is a big fan of rational interpolation through the Loewner framework, which that last example falls into that category, but also low-order interpolation. And we could have varieties of this where we interpolated first derivative or something of the transfer function. Here we just do first-order interpolation, collect left and right data by choosing some left interpolation points and some right interpolation points and some tangential directions on the left and the right. And then we just look at what our transfer function does. We pre-multiply by the left direction or the right direction, evaluating at the left or right points. We put those together in these structured matrices called Loewner matrices. And they turn out to obey the same kinds of factorizations that we require. And so we can use this in our machinery. And if you have your favorite method of collecting moment data or function data that fits into this factorization template, you could use this to create your own contour integral algorithm. All of these produce the same eigenvalues if used with exact data. But we're going to use these with inexact data, inexact measurements. And it's quite reasonable to ask how inexact measurements would affect the solutions. One tool for studying this would be to look at the pseudospectrum. I showed you a pseudospectrum of a matrix earlier. You can also define the pseudospectrum of a matrix pencil. So now we're allowing perturbations to our matrix A and our matrix E and a matrix pencil, and we're asking what's the set of all possible eigenvalues of these perturbed matrix pencils up to a certain level of perturbation on each of the coefficients. And so this gives one tool that you can use to study or compare sensitivity of different problems. This is an unstructured epsilon pseudospectrum. I'm not requiring that the perturbation maintain Hankel or Loewner or block Hankel structure, but this gives a kind of upper bound on that. And there are other ways of looking at pseudospectra for matrix pencils, but for looking at noisy data, this is the right approach. But there's something that kind of pops out that folks who developed these ideas pointed out early, that if you're allowing perturbations to your E coefficient that are larger than 1 over the norm of E inverse, that is to say the minimum singular value of E, then you can find a perturbation that makes E plus delta singular, which means that the perturbed pencil contains the point at infinity, which means the epsilon pseudospectrum would have to contain the point at infinity. So the minimum singular value of this matrix E and the matrix pencil really determines a minimum level at which you can do perturbation theory. If you want to make a perturbation above that threshold, then you have to be able to you have to have a more fancy tools at least, because you're allowing the possibility that a generic perturbation could give you any point in the complex plane, I think. Certainly the point at infinity. To control the size, we maybe want to control the singular values of our data matrix. And so you might want to choose interpolation points so that you can control the singular values of D. So just a few thoughts on the singular values of D. First of all, we know that Hankel matrices have very rapidly decaying singular values, particularly as we take the number of moments to be high. So that's a concern. And you can bound that in the case of symmetric positive definite Hankel matrices. Nice paper by Beckerman and Townsend doing that. Loewner matrices are matrices with low displacement rank, another topic of great interest to Professor Gohberg. And so that's a characteristic of fast singular value decay in some settings. And in particular, in the Loewner setting, you might look at how the interpolation points and their location proximity to the eigenvalues gives you faster or slower decay. You want to put your interpolation points in ways that give you slow decay of singular values of your matrix, of your Loewner matrix, because we're trying to identify that rank M. We don't want singular values of the Loewner matrix to decay into the noise floor where it's difficult to determine the rank of the matrix. And so I've done a little work on that with Cosmin Wonicha, and my student Alan Garcia has some nice bounds in his PhD thesis. And again, always reminding ourselves, why are we concerned about noisy data? Because it's not just rounding errors or something like that, it's quadrature errors that come from the fact that we're not exactly computing the data that we talk about. So here's just an example of how these different methods produce data matrices with decaying singular values and how we might determine the rank. This is another version of that problem, 6x6 problem I showed you earlier. We're going to take a contour integral discretized by these quadrature points in black. We'll choose Loewner points in red and blue. For Loewner interpolation, we'll choose a single point expansion at that blue star, just as parameters here. And we're going to try to find 21 eigenvalues that live in this region. That will be our goal, is to see, can we identify the rank 21 here? And what you see is a fair amount that depends on the quadrature precision. So here's, and this is a lot of eigenvalues to compute. Others might say, let's get smaller contours and compute only a couple eigenvalues at a time. But here, I'm trying to get 21 at once, and you can see if I don't have a very accurate quadrature rule, the singular values of the Hankel matrix may decay quite quickly. When we only have one sketching direction, we need many moments, and so that's one of the reasons you see that fast decay. That's 10 to the 40th down to 10 to the minus 20th. So that's 60 orders of magnitude spanned there. So that's quite a bit. But what's maybe disheartening is that we don't see a drop at the 22nd singular value that would reveal that this is a rank 21 matrix. If we go up to 1024 points, that's maybe a little bit clearer as we get increasingly, but it depends a lot on the dimensions of the sketching matrices and the number of moments we have and so forth. Similar kinds of results for that single point expansion, where, again, at low quadrature, you might not see any drop, but then as you increase the quadrature, you see a cleaner drop. One of the reasons we like Loewner methods is just they're so darn clean. Once you get up to a sufficiently accurate quadrature, you get a very nice regular drop. Again, our points were nicely spaced right around the contour here with our eigenvalues there on the real axis, and so it's a nice choice of contour points, but we get a very clean drop once we take enough quadrature rules, points. Okay, so in the remaining time, I'd like to talk about this application that gives me this example, waves on string networks. So this is a lot like the metric graphs that we saw last time, except in Pavel's talk, I think there was not so much importance about the actual orientation in the plane of edges to one another, but more their connectivity. Here we're going to think about a physical structure, a spider web, a network of vibrating strings where the angle geometry really matters and how these edges connect. And so here's a little inspiration from William Henry Hudson, a Victorian explorer. Now, I have repeatedly remarked that all spiders, when the shrill humming of an insect caught in a web is heard near them, become agitated, quit their own webs, and hurry to the point the sound proceeds from. By gently touching metal strings stretched on a piece of wood, I have succeeded in attracting spiders onto the strings with within 2 or 3 inches of my fingers. And I always noticed that the spiders seemed to be eagerly searching for something which they evidently expected to find there, moving about in an excited manner and looking very hungry and fierce. Spiders are computing eigenvalues, right? Or at least they're determining vibrations, right? And they're trying to understand, is it something to seek out or something to flee based on the way their web is vibrating, it's perhaps thought. Here's a simplest version, simplest interesting version, 3 strings that meet in the middle. And we want to study the eigenvalue problem associated with a string network that vibrates like this. Wave equations posed on those each individual string, and we can include material properties. We can allow the coefficients of the properties of the string to be inhomogeneous. We could add damping to this model and study what a viscous damping might do to the modes and so forth. So this is just the most primitive version, and the idea behind looking at this is to get a problem that might give us an interesting test problem for these contour integral solvers. So because it's just a wave equation on each string, even if it's in 2 dimensions, we obviously, just as in the last talk, we know the solution, just sines and cosines. And so we can write down a general solution on each individual piece, but then the boundary conditions will determine among all of the frequencies that satisfy the general formula of the solution, which ones also match up the boundary conditions. What's the secular equation, if you will. And so here we're looking at this particular symmetric 3-string, and we think about longitudinal vibrations, vibrations that can happen along each individual string, and then transverse vibrations that happen out of the plane of the string, the line of the string, just in 2 dimensions here. So we can impose those boundary conditions, and the boundary conditions that we get, Dirichlet conditions at the ends of the strings, but then a junction condition at the middle, where we have to get a smoothness there. We get 6 conditions that have to be satisfied. And if we look at what those 6 conditions are, we can model them as a nonlinear eigenvalue problem. This is a work done by my PhD student Jonathan Baker, who said this is just we don't need to discretize these strings, which Jennifer Green had done in a beautiful way in her master's thesis. Jonathan said, let's just solve the strings, and in terms of the eigenvalues, which we get from solving this nonlinear eigenvalue problem. Now, the more elements we have in the network, the bigger this becomes. This is just 3 strings giving us a 6x6 network, but you can see how quickly this can grow. This is similar to the dynamic stiffness matrix method of Wittrick and Williams, for example. So we turn a linear, infinite dimensional PDE problem into a nonlinear finite dimensional problem. This matrix has 3 kinds of eigenvalues. The first are just these simple transverse eigenvalues, and then longitudinal eigenvalues, and we can just write down the eigenvectors in a very simple way. There are infinitely many of these. Obviously, you can think of the roots of these 2 equations, right? Which omega satisfy them? Many, right? Infinitely many. So maybe it's a little alarming to see that there are infinitely many eigenvalues that have the same eigenvector. So one of the challenges of these nonlinear eigenvalue algorithms is that we need to be able to recover high multiplicity eigenvectors, or eigenvectors that are redundant, linearly dependent, associated with distinct eigenvalues. Then there's this double eigenvalue I mentioned earlier. It comes from a 2-dimensional subspace of solutions that satisfy this equation. And so there are the first 24 eigenvalues. That early example, I was looking for 21 of them with the singular values of the Loewner and Hankel matrices. Here are 24, including the double eigenvalues, some familiar numbers in there. Computed to high precision, not because the spiders care, but because maybe it makes sense to use this as a test case for numerical solution of these nonlinear eigenvalue problems. Here are the modes, and they're kind of fun to look at. We get these transverse modes, these type 1 modes that are just basically like sine waves like you'd expect for a simple string, and you've all shown your students. These longitudinal modes that all the motion is along the axis of the string, and then these hybrid type 3 modes that you can see where they get rather more interesting. And so those are the modes we're trying to compute. We're trying to compute vectors of size 6. Once we have that vector of dimension 6 giving us the coefficients, we can build these string models. Here's where they appear along the real line, and we see we're getting, at least on this portion of the spectrum, these double eigenvalues interspersing the single eigenvalues. We can choose some portion we want to compute, so we pick some there that we capture within that lasso. So that's a single eigenvalue, a double eigenvalue, single, double, single, double, single. So we get 4 single eigenvalues, 3 double eigenvalues. So we're looking for 10 eigenvalues. And Jonathan ran examples using these 3 different methods I've shown you. The classical approach using high order moments in this case, Hankel matrix with a finite shift and at 10 plus I, and then, and this is for a slightly different string than the one that I showed you, but, and then the right and left shifts with the Loewner framework. And what we see is, as we saw with the singular values, is the Loewner has the ability to kind of give you this nice drop-off, in this case in the eigenvalue error that's computed. And all of the eigenvalues that you compute in this case are found to very high precision with the Loewner method, whereas with the other methods, they tend to be a little less uniform. It's interesting, in the single point Hankel method, we chose our shift at 10 plus I, and the smallest error happens right around the shift, 10. And it gets worse towards the edges there. So Loewner allows us not to do high-order interpolation at infinity or high-order interpolation at some point mu, but rather to distribute the interpolation, first-order interpolation at many, many different points and get some balance there. You can do other fun things with this model. So you could take that angle at which the strings meet and you can vary that. Now you have a nice nonlinear eigenvalue problem that depends on a parameter, the angle the strings meet at, and you can do things like study avoidance of eigenvalues. So von Neumann and Wigner, classic work showing that there's often eigenvalues often come close but don't cross for these problems, and what you see here, Jonathan shows this nice modal jump. So even though the eigenvalues don't cross, it looks like the eigenvectors do, right? They seem to hop over the gap there. So the shape on the left matches the shape on the right on the other branch. One of the other nice aspects of this problem is that by adding symmetry, not just looking at a 3-string, but just adding as many branches as you like, you can increase the number of type 1 eigenvalues quite a lot. So here, if you have n symmetric strings, we had 3 earlier, so we had 1 type 1 multiplicity eigenvalue. But if you had 1, 2, 3, 4, 5, 6 of these strings, you would then get a 4-fold multiple eigenvalue. And so if you want to try to construct test problems for a numerical code that involves natural kind of degeneracies, this is a nice way to do it. Symmetries often lead to these kinds of degeneracies and can make a nice suite of test problems. Okay, so to wrap up, I think there's a rich connection between these contour integral algorithms in the numerical linear algebra world and the systems theory community, and that by looking at these algorithms through the lens of systems theory, one can realize that any system identification algorithm can be applied to these problems. The classical algorithms already have a lot of parameters to tune, and that's been, I think, an impediment to the development of robust software, though a number of different groups are working on that now, I think, or have worked on it. But even though we have now the ability to add more parameters to the problem with interpolation points, all of those different functions are so cheap to evaluate that we can go and do many, many different experiments, do the hard work of computing your resolvents, and then combine them and blend them in different ways and conduct experiments. And so if you have a large-scale problem that's really challenging, we can actually study whole classes of methods for very little work. As I said, we need more robust software that guides a user through how to tune these parameters and leaves less of that up to the user. It's easy to get bad examples by choosing your parameters wrong. And so how do you find the sweet spot that gives you the best performance? I think we have a nice set of test problems here for string networks, and that they also help because we can control the eigenvalue multiplicity and design monsters that will really challenge some of these algorithms and force them to use high moments and things of that sort. Okay, so with that, I would just like to thank the ILAS community, or the IWOTA community, for the opportunity to give this lecture in conjunction with ILAS, and invite you all to Blacksburg in May of 2026 for the ILAS meeting then. Thank you.